Okay, we have talked about the basic idea of RTL and of the notion of how we can synthesize RTL code, right? And the actual process by which we synthesize and look at the outputs of synthesized code, we'll look at examples as we move forward. But for now, I want to talk a little bit about how you should write code in such a way that you are likely to get something that will actually synthesize. There are a few general principles that you need to keep in mind. The first is write code that clearly represents the hardware structure. So this just again emphasizes what I have been saying all this while. You first need to know what your hardware structure is supposed to be, right? In other words, you probably end up with some kind of a block diagram that shows you roughly what your registers are, what your logic is, and how they connect together. And then you write the code that represents that hardware structure, rather than writing code, clicking a button and then saying I don't quite know exactly what it's doing. Right? That's always a recipe for disaster. You should be able to explain what your code is doing at the hardware level. The rest of it is more sort of conventions and coding styles. One of them of course is maintain a consistent coding style. Examples of that would be things like always using active low reset or active high reset, whichever is the convention being followed. Don't mix them. Similarly, don't mix POS-edge and neg-edge. Both are valid, right? You can get valid circuits with both of those. There are also scenarios, there are also other kinds of conventions where sometimes people require things like anything that is actually supposed to become a hardware register should be named with perhaps _R or _Q as part of its name. Now, these are again conventions depending on where you are finally writing your code, and if you are working as part of a larger group, the group might have certain conventions associated with it. So I don't want to really establish and say, okay, this is the only way you can write code, although I will be showing certain examples where perhaps things that potentially are nice to follow. That's all. Use synchronous design practices. This is not just to do with coding style. Synchronous design practices means the actual proper use of a clock and keeping that clean separation between the combinational update and the sequential logic, right? The combinational computation and the sequential update of the logic. By keeping that clear, it means that you have good synchronous design and it will all synthesize cleanly into a set of registers and computations. Explicitly declare all inputs and outputs, and also especially in terms of something like Verilog, make sure that all your wires are declared. Verilog has this unfortunate habit of implicitly assuming single bit wires for things that you have not declared. Make sure you don't fall for that trap. You should ensure that every single wire that you are using in your design is declared properly. And hierarchical design, right? As you would have noticed already, we are already looking at slightly more complex designs. We started out with things like gates, but then we went on to multiplexers, then adders, multi-bit registers, possibly loadable shift registers, right? That's more or less the most complicated circuit we have seen so far. But as you can imagine, what we are trying to do is we want to use those as components to build larger and larger systems, right? And that is the core idea of hierarchical design, and this is definitely a good way of going about doing design. Once again, to emphasize, know what hardware you want and write the code to get it, not the other way around. A few recommended practices, right? Use parameters. We already saw examples of this with the width of the shift register, for example, right? Implement one function per module. Now this function is not a Verilog function, right? What I mean by one function is one piece of functionality. So for example, if I want a certain kind of computation, maybe I've got some new kind of approach for computing square roots of numbers, right? I would have one module in Verilog whose only job is to take an input and perform the square root and give the output. I should not also then try to take that same module and try to make it do things like performing addition, multiplication, comparisons and so on. The exception to that of course is when I am designing something like an arithmetic and logic unit, where I am going to hierarchically compose. I will have single modules that do one function, one computation, but then I compose them together to get a larger module. But once again, that ALU, right, the arithmetic and logic unit, has pretty much only a restricted set of functionality. It takes certain inputs, it takes a opcode, performs a computation and gives you an output, right? So by having that kind of limited functionality associated with each module and then composing those together, it makes your hardware much easier to design and to debug. Keep combinational and sequential logic separate, use named port connections for clarity, document, right? The whole idea of how do you write documentation, how do you write comments, how do you explain your design process is something that can be sort of, I can give examples of certain scenarios, but at the end of the day, the only way that you can learn this is by actually looking at other people's code and practicing. Try it out, right? Write your documentation and your code in such a way that, think about it, if you were to read the same code, let's say 2 months down the line, would you be able to understand what you have written? That's one good way of starting. Okay. But documentation is something which once again doesn't fall directly in the realm of how we design, but is nevertheless a very important part of the design process itself. Now, when we talk about synthesis, right, as I told you, there are many constructs in Verilog that do not translate into hardware. So what I'm going to do is talk about a few of those and basically give you examples of things that are non-synthesizable, and pretty much anything related to time, right? Initial blocks that are present in code are not synthesizable. Okay, so initial blocks, in other words, should be present only in test benches. We know that test benches are not meant to be synthesized, they are only a simulation construct. So it's fine to have initial blocks inside a test bench, but in anything that you actually want to synthesize, an initial block is not going to work. Delay specifications, #2, #3, #0.5. As I told you, there is no accurate way of measuring time inside a system except in terms of clock edges, right? So a #2 nanoseconds, for example, is pretty much meaningless when you try to synthesize. Verilog has some very nice constructs in terms of wait statements, wait for a particular event to happen, or there are also so-called fork and join constructs which can allow you to sort of trigger off multiple independent threads of operation. The point is, all of this makes sense only in the context of simulation, right? Hardware doesn't really wait for something as such, right? The only way that it works is if a signal changes from one particular value to another, some computation happens, and as a result it might enable or disable a particular transaction somewhere else. So it's not as though I can actually tell hardware wait for this and it will actually automatically create the logic to wait for it. Okay. So in general, the wait statement in Verilog is not synthesizable. As you might imagine, anything file related is non-synthesizable, right? So read mem, display, monitor, file IO are not synthesizable, except in some very specific scenarios. In some cases, depending on the compiler, right, not all compilers support this, it may be possible to initialize an array, a ROM so to say, by reading values from a text file, right? And that is actually a scenario where an initial block can be successfully used inside a Verilog synthesizable module as well, right? Effectively, that entire initial block, as long as it only consists of reading some values and populating a memory or something, will be processed away. It will not translate into something that actually happens at runtime. At compilation time itself, an array is created which contains the values that you want. Having said that, this occurs only in very specific kind of scenarios. As a general rule of thumb, these are not synthesizable. Variable types, right? Verilog does have support for integer, which is actually synthesizable because it just pretty much treats an integer as a 32-bit value. But it also has a few other data types including real and time and so on, which, as you might imagine, don't really have a physical meaning, and or rather not in the sense of digital hardware, and therefore cannot be directly synthesized. In particular, one of the things that you need to watch out for is there is a way by which you can implement floating point computations in hardware, but that's not by writing real as a data type in Verilog. It does not work that way. A couple of examples of bad code, so to say, right? As you can see over here, what is going to happen in this case is I have got an always at star, essentially an always comb, right? I am sort of saying that I want it to be a combinational logic. But if I look at the if statement, I am basically saying that, if select is high, out should be equal to A. But what happens if select is low? I am not specifying what the value of out should be. So this is kind of tricky. This seems to indicate that I want combinational logic, but at the same time I am not specifying what to do when select is low. And the only thing that the system can do as far as the simulation is concerned, what would happen is when select is low, I simply would not change the value of out, and therefore out would have whatever value it last had. But in hardware, that's not what's going to happen, right? There's no way that I can get that kind of behavior unless I explicitly bring a latch into the system. Hardware does not have a notion of the last value that was written into out unless you bring in a latch or a flip-flop to bring memory. Okay. Bottom line is, this is badly written code. This is almost certainly not what you wanted, right? What should happen instead is give it a default value which says that if select has not been done, then what should the value be, and this is fine. It can basically create a combinational logic out of this. Similarly, you could have a case statement instead where I have what to do when the select signal is 0 0 or 0 1, but I don't have a default condition which I have added here. Over here I say that if it doesn't match with any of the cases over here, just set it to 0, and that's fine. Once again, this can get translated into a nice piece of combinational logic. It's essentially a multiplexer, right? But at least it will synthesize and the way that you want. So a few best practices over here, right? In general, always provide default assignments, use complete case statements, right, with the default. Now this is not a complete case statement, but it does have a default condition, so that's good in that sense. Initialize all variables, an example is out here, right? And there are a couple of other constructs in Verilog, notably the case X and case Z or case Z. What those say is that you can actually put in X or Z values out here to indicate that if during the simulation one of those values is unknown or is tri-stated, how should the system behave? Now that's not a good idea. Well, case X could potentially be used in order to simplify your logic a little bit. Case Z is almost certainly not synthesizable in the sense that there is no reliable way of detecting that something is at a high impedance state, right? So bottom line is, most likely that is not what you want when you are actually trying to synthesize your logic, and therefore just avoid it in your code to start with, because most likely it is not going to synthesize into something that you expect. Okay, moving forward, let's look at a few ways by which we can actually write code, right? And this we have already seen is the recommended way of writing a synchronous register. It's the most basic form of register, right? We have an always at POSH clock, or you could write always underscore FF preferably, right? Here you will notice that I am using if reset or if RST, right? It is not active low, in this case it is active high. That is, whenever RST is equal to 1 is when this condition is going to get activated. When RST is 0, Q equal to D will happen, which means that in your test bench you need to make sure that the RST is initially set to 1 and then it's taken out. Again, a potential source of confusion if you keep mixing RST and RST underscore N. This convention at least helps you remember what is what, but it's always preferable not to try and mix the two together, right? Use appropriate naming and make sure that you sort of stick to one convention for your entire design if you can. A few guidelines: use non-blocking assignments, but at the same time use blocking assignments for combinational logic, right? We already saw examples out here. All of this is combinational logic, and here we are using blocking assignments. We don't want non-blocking because it's not even clear what exactly that means in the context of combinational logic, right? In combinational logic, we are just saying, okay, I need to perform a sequence of computations, and if I have a sequence like that, then essentially what it means is take the output of the first step, connect that physically to the next logical gate, connect that to the next logical gate, and so on until I have the final output, right? So that makes sense to have blocking assignments, so to say. Non-blocking makes sense when you have a clock and you want to be able to say that there is a concept of a previous value. No matter what, avoid mixing blocking and non-blocking assignments inside the same always block. There is never a good reason to do this. And again, as a matter of convention, keep the reset logic synchronous when possible, right? This basically means don't have the or POSH reset over here. Now this is, as I said, a little bit more sort sort of domain specific, especially in the context of FPGAs. It turns out that synchronous resets are easy to implement and actually are good in certain ways, right? But there could be other kinds of designs where asynchronous resets are necessary for various reasons. Okay, so continuing on a few patterns of logic that we have. Once again, this is an example of a flip-flop with an enable signal, right? All that we have done is added an else if enable to say only when the enable signal is high should it act like a flip-flop. Effectively, if enable is low, then even if there is a transition on the clock and I am not in reset, it will still hold the last value it had. This is perfectly fine. This is a legitimate use of a flip-flop and can be used for sort of gating condition, which says only when this condition is satisfied should the value of this flip-flop change, right? Very common kind of scenario that we use all the time in practice. Shift registers, we have already seen what happens, right? So I can have a shift register where I basically say take the LSB values, shift them and pad it out with some kind of data input to make it effectively shift into the least significant bit. Now, I've talked a couple of times about synchronous versus asynchronous reset. I just want to say a little bit more about that. As you can imagine, in the asynchronous reset, we do not need to wait for the clock, right? What we are saying is any time that the reset signal comes in, it overrides whatever is the present state of the flip-flop and just forces it usually to 0, although you could have a sort of set or reset. So you might have instead of a reset to 0, you might potentially have a scenario where you are actually forcing it to 1 under the reset conditions. Now, the important point is that this asynchronous reset is critical for usually for power on scenarios, right? Why is that? Because the way actual circuits work is that it's not that as soon as you switch on the system there is a clock and the system just starts working. The clock is also an electrical circuit which takes a little bit of time to sort of ramp up and stabilize and actually get to the correct frequency and have the correct sort of square wave behavior that we expect from it. Now, how much is that time? Typically it might be on the order of maybe microseconds or at most milliseconds, but there is a certain amount of time associated with it, which means that during that time, or it could be even less, it could be like a fraction of a microsecond, but it doesn't matter. It's typically still something which is large enough that that it is more than perhaps the clock period associated with the actual clock itself. This is usually related to one phenomenon called the locking of a phase locked loop, and phase locked loops are critical components that are used for essentially supplying clock signals throughout circuits. How exactly they work is not relevant for us. What matters is that they do take a certain amount of time to lock, which means that if the PLL has not yet locked, you do not have a stable clock signal, and during that time it is in general always better to hold your circuit in reset to prevent the chance that it arbitrarily starts performing certain computations, or even worse, activating signals which could in turn actually activate something outside your circuit, right? The worst case scenario is, let's say you are trying to control the motor of a car, and because you did not reset it properly, when you just switched on the car, the first thing that happened was that it turned on the engine at full speed and made it crash into a wall, right? So you always want to make sure that your electronics has first sort of stabilized before it has a chance of actually interacting with the outside world. In such a scenario, asynchronous reset is crucial. The problem with asynchronous reset is essentially related to timing analysis. That's one of the biggest problems. Timing analysis is something we'll be talking more about later, but it is something that needs careful design, right? It can lead to something called metastability. Again, something that we'll be talking about later. Metastability occurs when you have two signals changing too close to each other. And in general, something like this tends to require separate routing resources in terms of your hardware, right? On the other hand, synchronous resets turn out to be much easier from the point of view of timing analysis. They are more or less like any other regular signal that can be routed using the regular routing logic that is present inside an FPGA, for example. And especially for high speed designs, it turns out that it leads to a cleaner analysis. You don't have so-called asynchronous paths, and all your timing analysis can be done in a uniform manner, right? What exactly is timing analysis is something that we will be looking at in a little bit more detail later. Now this is more of a subjective issue, but there is an argument that can be made that says that this leads to sort of cleaner designs in some sense, right? Mostly related to the fact that you do not have these long reset wires all over the place that need to be routed in a different manner than the regular other wires that you have. The obvious flip side of this is the exact problem that was solved by asynchronous reset. Unless the clock is stable, the reset is not even going to work. It does not have a chance of forcing your outputs to a known state, right, until the clock has become stable. It may also end up using extra logic. You saw the example I had where you use an AND gate to essentially enforce the resetting condition, right? And releasing the reset typically takes an extra clock cycle. You need to wait until the reset has activated and then sort of, so one clock cycle has to pass and only then you sort of take it out of reset. Now, is that going to be a problem? In most cases, not necessarily, but it is a consideration, right? So having said all of that, because of these benefits, especially at the module level, where you are not necessarily dealing with the outside world directly, it is always preferred in terms of FPGA designs especially. So let's look at a few examples of synthesizable code and non-synthesizable code, right? What we have over here is an example where I have pause edge clock and I am trying to do #2, #3. Basically these things don't synthesize. What will happen in most scenarios is that the tool will just ignore these delays, give you a warning saying that it's ignoring the delays, and then proceed to synthesize as though this did not exist. So it may not turn into an error, which in some cases is actually worse. It ends up generating something which your simulation would give you a different result than what your synthesis is going to finally give you. On the other hand, simple logical code like this is easily synthesizable. Once again, initial blocks, right, where I try to set the initial conditions, counter equal to 0, state equal to idle, doesn't work because there is no concept of initial except if I have an explicit notion of a reset, right. If I bring in an RST signal over here, then that's easy. I can actually say counter equal to 0, state equal to idle when the reset condition is applied, else go through normal operation. This is how you do initialization in the context of actual synthesizable hardware. Now a few examples of mistakes that can happen when you are writing code, right. Code like this where, for example, you notice that there is an out signal over here in one always block and another out signal in another always block, right. It's the same signal because after all it's the same name, but now depending on different conditions it is assigned different values. Now this is actually a scenario that you might end up writing. I have encountered scenarios like this where it seemed like the logical way of writing code was to just have the same signal being assigned in two different always blocks. Now if you think about it from a hardware point of view, that doesn't make sense, right. I cannot have a single wire being driven by two different blocks unless I am going for something like a wired OR or a wired AND connection, which is not what we are trying to model in Verilog in general, right. What should be done instead is something like this. I should have a clear picture of when I want out to have the value of in1 and when I want it to have in2, and that condition should be put into a single always block. Right? This takes care of the problem for me. Whatever I had over here, it should be possible to find a condition that says they are mutually exclusive and then decide one or the other, right. The only scenario where you absolutely need something like this is a condition where both this as well as this might be true, right, and that just basically sounds like bad news, right. For example, let's say in1 and in2 change at the same time, both of these blocks are going to get triggered and out doesn't know which value to take. So I definitely need some kind of logic like a select operation which tells me which one is actually supposed to take precedence. Same way, I have missing signals in my sensitivity list. We have been over this before. This will essentially end up in something like a latch. The easy solution for that is don't even do that, either use always comb or always at star. What about missing assignment types or mixing assignment types over here? What you can see is, I have one blocking assignment and then I have a non-blocking. It seems to make sense. This is sort of supposed to perform a combinational computation followed by an update out here. It doesn't work because this non-blocking assignment essentially means that the order that I was expecting to see over here may not necessarily happen, and what I see in simulation and what I get in synthesis may differ. In this case, it looks as though what I want to do is basically take the value a plus b and assign it to q. So why not just go ahead and just have it as one single non-blocking assignment out here, right? Alternatively, take assign temp equal to a plus b as something outside this always block, and then assign q equal to temp or non-blocking q equal to temp inside the always at passage clock. That also works. An example where things are getting too complicated, right? You have an always block which you are trying to make combinational. It has many states with some kind of complex logic inside them, and you are writing a case statement of this sort which basically has many states and fairly complex logic in here, right? The alternative is to sort of simplify this logic. You have over here typically what ends up happening is I have certain kinds of computations based on the present state. The cleaner way of doing it is to say, okay, let me explicitly think of my present state and my next state. I have my present state, I'll write a code which only encodes state transitions out here. And this is related to finite state machines, which we will be talking more about later, but you already know how finite state machines work, right? They have transitions between states. So have an always block whose only job is to encode those transitions. That makes it very easy to look at this always block and understand exactly what the FSM structure is. Have a separate always block that takes care of computation of outputs, and this essentially makes your logic easier to understand. It may potentially also solve problems where you are actually writing code like this could potentially even result in a non-synthesizable system, whereas this would actually cleanly split it out into two separate parts. So sort of the key points, the summary out here, the synthesizable code is a subset of all of Verilog, right? Not all Verilog translates into hardware. The important point is there is no substitute for designing at a high level of abstraction, right, or in abstraction in general, right? First design at the block level, make sure that you know what your register transfers are supposed to look like, then write the code for that. And always understand, so this is where sort of having a reasonable understanding of how compilation works is important for a designer. At the end of the day, you need to know what kind of patterns in your code are going to translate into what kind of patterns in hardware. And this is to a large extent dependent on the type of hardware design or the compiler that you have, right? There are compilers that try to go out of their way to accept any kind of code and actually synthesize them in some way. I'm not necessarily sure that's a good thing. It's always better if they sort of fail early and say, look, this code doesn't make sense, so you shouldn't be writing code like this. Can you clarify what you are trying to do? Okay. But from your point of view as a designer, you should always think in terms of understanding how these patterns get compiled and how do you write them in such a way that you can actually get efficient and good code.